Hello everyone. In this video, we're going to start a new topic in this course. And that new topic is one of the most important topics of the course, and it also happens to be one of the more challenging topics of the course. And this topic is called functions. Now, I've mentioned the word function quite a few times in this class. You've probably read about it, and you've actually been working with functions and may not even have realized it. For example, every program has a main function. So when you write int main curly bracket, that is the definition of a function. We're going to learn about why functions are useful in computer science, why programmers might use a function that somebody else has written, why we might define our own functions and use those. And we're also going to talk about top-down design and how we can come up with a good design for our program that uses functions. So let's head over to the notes, and we'll see that we have a warm-up task called opening a file called gpa-computation-fun.cpp and coding up an empty main function. In gpa-computation-fun.cpp, we're going to work a review problem of the topics we've covered so far in the course, and then we're going to see why our solution really lends itself well to functions. And then we'll redesign our implementation to use functions. So the example problem that we're going to code up is computing the average grade point for a user. So we're going to have the user enter information about their grade point for 3 different courses. So here's our input. We're going to need the grade point and number of credits for a course, call it course 1, grade point and number of credits for a course 2, grade point and number of credits for course 3. So that's 6 different pieces of information, 2 pieces for each course that we're going to need. In order to compute a grade point average, a GPA, you have to multiply the grade point for each course by the number of credits of that course to weight it. Then you sum all of the weighted grade points and divide by the total number of credits. Here's the formula here. So our output will be the grade point average. So this will be kind of a simple solution. We're not going to use any files. We'll just use all of our input from the user, and we'll only do it for 3 courses, but you could see how even to compute your GPA for 1 semester, you would likely need more input than that for 3 courses. So here's our algorithm that we're going to use to solve the problem. Get the grade point for each class, get the credit hours for each class, compute the credit hours earned, so this would be the numerator, compute the total number of credits, this would be the denominator, and then divide the numerator by the denominator, credit hours earned divided by total number of credits to get the average, and then display the results. So my task for you is to go ahead and code up a solution using this algorithm. This algorithm doesn't require any conditional, any loops, or any files, so it should be pretty good review of some of the earlier topics of the course. So do pause the video now and work on that task. Your solution probably looks something like this code that I've listed under implementation. I'm going to go ahead and just copy this for the sake of time and paste it inside of my GPA computation fun.cpp program. So I'm going to run this so you can see what it looks like. So let's say you're awesome in computer science, you get a 4.0, that's a 3-credit class. And then maybe for your math class, pretty good, but not so hot. Maybe that's a 4-credit class, and then a 4.0 in your 1-credit karate class. And then it tells you your grade point average for these 3 courses. Okay, so the reason why I wanted you to solve this problem is it's a great review, but it also has a lot of built-in redundancy. For example, let's say I wanted to change the prompt for, let's say, entering the number of credits so that it says something like, please enter the total number of credits. Or instead of using the word number, maybe using the pound sign. Just some sort of small change. You would have to change this in 3 spots because there's redundancy here. At some point, you probably copied and pasted this prompt in order to get a prompt for the math course and prompt for the karate course. So now if we want to try and maintain this program by making some small changes later, we're going to have to make changes in multiple spots. And the more changes we have to make, the more likely it is we could introduce a bug into our program. Now let's take a look at all of our variables we have up here. GP1, GP2, GP3, num credits 1, num credits 2, num credits 3. This is 6 variables just for 3 courses. Let's say we were going to write this program such that it would compute the GPA for an entire college career, 4 years worth of classes. First off, that would be a really slow program if you had to manually enter all that information. You probably would read it from a file instead. But regardless, you would have to have Okay, so we've seen that if we needed to make a small change to the prompts, we'd have to do it in n number of places where n is the number of courses that we're going to read information for in. What about these pairs of C out, C in, C out, C in, C out, C in, so on and so forth? There's redundancy there as well, right? We have the same sequence of code where we prompt, get a value, prompt, get a value, so on and so forth. If we could somehow just write that code one time and then put a label on it that says this is the code that gets the grade point from the user, or this is the code that gets the number of the credits from the user, then we could just call that code to say go execute it, go execute it, go execute it, instead of having to copy and paste it and introduce redundancy in our program. So these few reasons about why this code is redundant really helps motivate why we want to use functions in our code. So when talking about functions, I first want to introduce something called top-down design. Top-down design is a way to manage the complexity of a problem by decomposing it into smaller, less complex subproblems. While we're going to use top-down design to break problems down into small subproblems that we could write a function in order to solve, you can think about top-down design as being applicable to problems outside of computer science. You might end up using top-down design in order to solve problems that have nothing related to programming, just because it's really useful for breaking a large problem down into smaller, more manageable tasks. So each one of these smaller, more manageable tasks, if we can make them small enough, could really be implemented using something called a function. Now, a function is a named sequence of instructions that solves a problem. Let's go ahead and write that on the board. You'll notice that this definition sounds a lot like the definition for an algorithm. The definition of an algorithm is a sequence of instructions that solves a problem. So with function, there's kind of this emphasis on naming that sequence. So with top-down design, we have this large problem. For example, how do we compute the average GPA or grade point for a user based on all of their course information? That's a large problem. But we could break it down into individual tasks that we could write one function, one algorithm to solve. When we break a task down into a function, that function becomes a reusable piece of code that we can use over and over again. For example, if we have a function perhaps called getGradePoint, and all getGradePoint does is prompt the user for a grade point, get the grade point from the user using a cin statement, then we could call that function or use that function 3 times. One for our computer science course, one for our math course, and one for our karate course. It solves a very specific problem, and that solution is reusable. So top-down design is really just an approach that we use in order to help us figure out what these functions are we should implement. So continuing with our GPA computation fun example, we can visualize top-down design with a structured chart. Here's a structure chart for our GPA problem. At the top of our structure chart, we have the whole problem, the big problem. Ours is we want to compute the GPA for a user. Then we break down our problem into a sequence of smaller problems until we've broken the problem down into its smallest form, most simplest form of a problem. So in order to compute the GPA, we've got to get the grade point for each class and credits, we've got to compute the GPA, and we've got to display the GPA. Now, for each one of these subproblems, there are a few more subproblems. For example, get the grade point for each class and credits means we could have a function called getGradePoint, and it contains all the code necessary to get the grade point from the user. We could have a function called getCredits, and it contains all the information to get the credits from the user. In order to compute the GPA, we need to first compute the numerator, which is the weighted credits, and then we need to compute the total credits and use both of those values to compute the GPA. Then to display the GPA, well, that really can't be broken down into another task. That is a small functional unit in itself. So we might have a single function that contains the code necessary to display the GPA. Structure charts are really useful for applying top-down design to help break a problem into smaller problems that each can be solved by writing a function. In the next couple of videos, we're going to write these functions here so you can get your feet wet working with top-down design, structure charts, and functions.